Repetition is often dismissed as boring or mechanical, something required only when understanding fails. But repetition is not a fallback strategy. It is the primary method through which the brain encodes skill, memory, and automatic behavior. Without repetition, nothing becomes fluent. No language is spoken effortlessly. No instrument is played without thought. No physical movement becomes coordinated. What feels like tedious practice is actually the brain constructing pathways that will later allow tasks to happen without conscious effort. This video explores how repetition shapes the brain, why it works, and what changes inside the neural architecture when something is repeated over time. The first encounter, fragile and effortful. When the brain encounters something new, the experience is fragile. A new word, a physical movement, a concept, each leaves only a faint trace. The neural activity required to perform the task is scattered. Multiple regions activate, and the process feels slow and deliberate. This is not because the brain is struggling. It is because the brain has not yet determined which connections matter. The first time a person attempts to play a chord on a guitar, their fingers move awkwardly, the hand positions feel unnatural, and the sound produced is imprecise. The brain is recruiting many more neurons than necessary, testing different motor pathways, searching for the most efficient route to the desired outcome. This initial inefficiency is essential. It allows the brain to explore multiple strategies before committing resources to one. The second and third repetitions, pattern recognition begins. With the second and third repetitions, something begins to shift. The brain does not experience the task as entirely new anymore. Certain neurons that fired during the first attempt fire again, and the brain begins to recognize a pattern. This is the beginning of encoding. The scattered neural activity from the first attempt starts to cohere. Connections that were irrelevant begin to weaken, and connections that contributed to success begin to strengthen. This process is called synaptic pruning and potentiation. Synapses that are used repeatedly become more efficient, while synapses that are not used fade into the background. The brain is not simply remembering the task, it is sculpting the network that will perform it. After a few repetitions, the guitar chord still requires conscious thought, but the fingers hesitate less. The hand position feels slightly more familiar, and the sound improves incrementally. The brain is beginning to automate small components of the larger task. Continued repetition, building myelin and efficiency. As repetition continues, a biological change occurs at the cellular level. Neurons that fire together repeatedly trigger the production of myelin. Myelin is a fatty insulating layer that wraps around the axons of neurons, the long fibers that transmit electrical signals from one neuron to another. Without myelin, signals travel slowly and with inconsistency. With myelin, signals travel faster and more reliably. Think of it as upgrading from a dirt path to a paved highway. The route remains the same, but the speed and consistency of travel increase dramatically. This process of myelination is not instantaneous. It requires repeated activation of the same neural pathway over days, weeks, or months. Each repetition adds another thin layer of myelin, incrementally improving the speed and precision of the signal. This is why skills improve gradually rather than suddenly. The brain is not switching from unable to able. It is transitioning from slow and inconsistent to fast and reliable. A pianist does not wake up one day able to play a difficult passage. They practice it hundreds of times, and with each repetition, the neural pathway becomes slightly more myelinated, slightly faster, slightly more automatic. The shift from conscious to automatic. At a certain point, repetition allows a task to move from conscious control to automatic execution. This shift is profound. Tasks that once required deliberate focus begin to happen without thought. The brain is reallocating responsibility from the prefrontal cortex to subcortical structures like the basal ganglia and cerebellum. The prefrontal cortex is responsible for conscious, effortful control. The basal ganglia and cerebellum are responsible for automated sequences and motor patterns. When a skill becomes automatic, it no longer consumes the same cognitive resources. This is why an experienced driver can navigate a familiar route while holding a conversation, or why a fluent speaker can construct complex sentences without consciously selecting each word. The task has been handed off to systems that operate below conscious awareness. This does not mean the brain has stopped working. It means the brain has optimized. Repetition without attention, shallow encoding. However, not all repetition leads to deep learning. Repetition without attention often produces shallow encoding. If a task is repeated mechanically, without engagement or variation, the brain does not invest heavily in refining the pathway. The connections may strengthen slightly, but they do not become optimized. This is why rereading a textbook passage 10 times without thinking deeply about it rarely leads to retention. The brain is detecting familiarity, but it is not encoding meaning. True learning through repetition requires some degree of active engagement. This does not mean every repetition must be effortful, but it does mean the brain must recognize the task is relevant. Variation within repetition is often more effective than identical repetition. Practicing a musical phrase at different tempos or solving similar math problems with slight differences forces the brain to generalize the skill rather than memorizing a single fixed sequence. This creates a more flexible and robust neural pathway. The role of spacing and consolidation. Repetition is also more effective when spaced over time rather than massed in a single session. The brain consolidates learning during periods of rest, particularly during sleep. When a skill is practiced, the neural connections are activated and strengthened. But the deeper integration of that skill happens offline, when the brain is not actively engaged with the task. Sleep allows the brain to replay recent experiences, reorganize neural networks, and solidify new connections. This is why distributed practice, practicing a skill across multiple days, is generally more effective than cramming all practice into one session. Each practice session creates an opportunity for consolidation. The brain is given time to process, refine, and strengthen the pathways before the next repetition. Repetition and error correction. Repetition also allows the brain to detect and correct errors. The first few attempts at any task are rarely perfect, but with each repetition, the brain receives feedback. Did the movement produce the intended result? Did the word choice convey the intended meaning? Did the calculation yield the correct answer? This feedback is used to adjust the neural pathway. Connections that led to errors are weakened, and connections that led to success are reinforced. Over time, the brain becomes more accurate, not because it is trying harder, but because the pathway itself has been refined through repeated feedback. This is why practice often feels frustrating in the early stages. The brain is still calibrating, but as repetitions accumulate, the errors decrease, and the task begins to feel smoother. The plateau effect, when progress seems to stall. At some point during repetition-based learning, progress often appears to plateau. The initial improvements are rapid, but after a certain number of repetitions, gains become smaller and less noticeable. This is not a sign that learning has stopped. It is a sign that the brain is refining details rather than building new structures. The major neural pathways have already been established, and now the brain is optimizing them. Myelination continues. Synaptic connections are fine-tuned, and the skill becomes incrementally more precise. These changes are harder to perceive, but they are still happening. This is why experts continue to practice even when improvement seems invisible. They are maintaining and refining pathways that have already been built. Why repetition feels different over time. One of the most interesting aspects of repetition is that the subjective experience changes. The first repetition feels novel and requires full attention. The 10th repetition feels familiar but still effortful. The 100th repetition feels automatic and almost thoughtless. This shift in experience reflects the underlying neural changes. As pathways become more myelinated and efficient, less conscious effort is required. The brain has offloaded the task to systems that operate with minimal cognitive cost. What once demanded focus now happens in the background. This is why experienced practitioners often describe their skills as feeling effortless. not because the brain has stopped working, but because the work has become invisible. Implications for learning. Understanding how repetition shapes the brain helps clarify why certain learning strategies work. Short, focused practice sessions spread over time are more effective than long, infrequent sessions. Variation within repetition builds more flexible skills than rigid, identical repetition. Active engagement during practice deepens encoding more than passive exposure. And progress that feels slow or invisible may still represent significant neural refinement. Repetition is not about forcing the brain to memorize. It is about giving the brain the time and exposure it needs to build, refine, and automate. Closing reflection. Repetition is not a workaround for difficulty. It is the mechanism through which the brain transforms conscious effort into automatic competence. Each repetition adds another thin layer of myelin, strengthens another synaptic connection, and brings the task one step closer to fluency. The process is gradual, often invisible, and sometimes frustrating, but it is also inevitable. With enough repetition, the brain will encode the pattern. The question is not whether repetition works, but whether the learner is willing to trust the process long enough for the changes to take hold. And once that trust is established, repetition stops feeling like tedium and starts feeling like construction.